Okay. So at one level, you can say that the Fourier transform comes as a limiting case of the Fourier series. It kind of looks like this. The other way is to say the Fourier transform is defined in this way. Just don't ask me why. Just it is this way because that's the way we want to define it. And again, in math, it's perfectly allowed to do. You're perfectly reasonable in doing that. Okay. There are many other transforms. Fourier is not the only one. We'll talk about Laplace, but there are also Mellin transform and various other transforms which are defined. You say by definition, this is the transform. Don't ask me why. And then I'm going to show you some properties about it. And then when you have the properties, then you can use it for various things. But why it is designed in a particular way, there's no point. It's just we define it in a way because you want to. Okay. However, in this class anyway, I'll try and give you intuition about all the different transforms, why they arise. In this particular case, hopefully this part is clear. And then now we can sort of forget where we came from, okay, and just focus on this particular form, xj omega, this integral minus infinity to infinity, xt e to the minus j omega t dt. Okay, and then notice that this is a function of omega, not a function of time. Okay? Any questions about this right here? Okay, so now let's use this form and just essentially plug and chug, and we'll do some examples. So let's do Fourier transform of a pulse. Because this is sort of the easiest case. So we have a pulse, and let's say it's centered at 0 and it has a width of tau. Okay, that's the pulse. Then that's xt. And they say, what is xj omega? So x of j omega, by definition, is given by minus infinity to infinity, xt e to the minus j omega t dt. And this is going to be minus tau over 2 to tau over 2 e to the minus j omega t dt, because it's 1 over here. And this is nothing more than e to the j omega tau by 2 minus e to the minus j omega tau by 2 over j omega. And we notice this as being the sine function, the sine x by x, and if with a little bit of simplification, we get essentially tau sinc omega tau by 2. Okay. Okay, so this is, this is going to be sine of, sine of omega tau by 2 over omega, and you just multiply both sides above and below by tau over 2, so you'll get sine omega tau over 2 omega tau over 2, and then this will go, obviously you get this form over here. And so this is basically the Fourier transform of a single pulse, and it looks, what does it look like? It's a sinc function. So we get the sinc function again. Something like that. And these zero crossings, we're going to be at minus 2 pi. So there's a 2 pi by tau, and this is minus 2 pi by tau. Why? Because we want omega tau by 2 equals pi, equals m pi. So which implies omega equals 2m pi by tau. And so we get, first one is at plus minus 2 pi by tau, 4 pi by tau, 6 pi by tau, etc. So 2m pi by tau is when the zero crossings are, right? And so the first homework question was, at what values of omega does a pulse with width 2 microseconds have no energy? Okay, that was the question. So, well, let's see that. So we need, what do we want? We want omega equals 0, which implies omega equals 2m pi by tau. Those are the frequencies, right? So what is tau? Tau equals 2 into the 10 to the power minus 6. which means that omega equals m pi times 10 to the 6, because the 2 cancels out. And so that's the answer, radians per second. M pi times 10 to the 6. So it's to get a better understanding of this, if you just substitute the value for this, then we can write this. So we can write this as this. So we know that 2 pi radians equals, radian per second equals 1 hertz, right? Because in 2 pi radians, you do 1 complete rotation of the phasor, that's 1 hertz, 1 cycle per second or 1 hertz. That's the conversion formula. So that one can be rewritten as m pi by 2 megahertz. Okay, that's m pi by 2 megahertz is where the zero crossings are. Okay, so the first one is going to be at about 1.8 megahertz, and then 3.6 megahertz, sorry, not 1.8, so pi by 2, 3.1, so 1.5 something, 1.55 megahertz, 3.14 megahertz, etc., right? And so that's where these guys are going to be. These crossings are going to be at these points over here. So it's actually at megahertz range. So why is this important? It means that if I send a pulse of width 2 microseconds, okay, I can tell you that, now I didn't tell you at what quote unquote frequency band I'm sending it at. Remember, I have a carrier frequency, right? I have a carrier that's underlying it. If in the carrier I'm going to inject a pulse of 2 microseconds, what will happen is that the carrier is not going to have any energy due to that pulse at the frequency band that is 1.55 megahertz away from the pulse, okay? Which means I can put in another signal, okay, something like this, another sync pulse, which is centered over here, and what will happen is its energies will be such that they're centered at the 0 points of this particular pulse. Okay, and I'm not really drawing it very well, but intuitively what's happening is that the pulse, which lasts 2 microseconds, in the frequency range, the frequency domain has these frequencies which has no energy, so I can put a pulse in there, okay, with that carrier. Okay, I can put a carrier in that range. When I put it there, it's not going to have any, it's not going to see the other one, because it's just kind of invisible. And so generalizing this, and I'm going to wave my hands here, it is possible for us to come up with a set of frequencies, okay, such that pulses sent on these frequencies don't see each other. And these particular frequencies are called orthogonal frequencies, and that's the basis of what's called orthogonal frequency division multiplexing. So we have, instead of a carrier, we have what are called subcarriers. Typically you'll have 4, 8, 16 subcarriers, and in each subcarrier you'll put a different signal, and magically they don't see each other. Why? Because we know that the sync function has 0 crossings at these energy bands, at these megahertz. So this homework example actually gives you the idea of what you could do, and this is a huge thing. The fact that just essentially really trivial analysis can give you the idea that there is 0 energy locations, and now you can use those, now means that in one piece of spectrum, okay, one spectrum band, we can actually send a lot of information. And if you look at all modern communication systems, okay, cell phones, Wi-Fi, which is really the 2 main things that are out there, plus pretty much anything else, or the Zigbee, you name it, they all use OFDM, orthogonal frequency division multiplexing, because you're getting something for nothing. Okay, in some sense, you're getting something for nothing. Because spectrum is very expensive. Okay, spectrum is the electromagnetic spectrum is limited resource. You just have a certain amount that we have, and each piece of it is very valuable. Okay, I don't know how many people know this, but do you know how valuable it is? Okay, so a chunk of spectrum, which is a couple of megahertz width, or a couple of megahertz width at the right frequency band, like 700 megahertz, is worth, just in Canada alone, is going to be worth about $4 billion. It's not a million, but $1 billion. In Europe, they auctioned off that kind of chunk of spectrum for $40 billion about 10 years ago. Okay, $40 billion. So spectrum is super expensive. Okay? We always do these bids in billions, not in millions. Because once you have it, it's like owning beachfront property, okay, in Florida, which is great until the water level rises. Okay, it's very, very good. So suppose somebody comes in and says, here, I'm going to give you a plot of land in Toronto. You can build whatever you want over there. You can build a skyscraper and sell off it. How much is it worth to you? It's worth a lot because that's a property. That's where it is. It's good property. If somebody says, I'm going to give you 1 square kilometer in the middle of Nunavut, okay, you probably don't want to pay too much for it, because it's kind of cold and frozen all the time. So as a footnote, what we have today, Wi-Fi, is actually in Nunavut. Okay, nobody wants it. The 2.4 gigahertz band is the band which is the water absorption frequency. Okay, water absorbs at 2.4 gigahertz. If you hit a bottle of water at 2.4 gigahertz or 5 gigahertz, it gets warm. Okay, it's called microwave. That's what happens. You hear microwave oven? You put food in it, it's being hit with 2.4 gigahertz, actually it's being hit with 5 gigahertz radiation, and the water molecules get excited by that radiation because why? It's a natural frequency of water molecule. Remember we talked about resonant frequencies and natural frequencies? Water molecules, resonant frequency is 5 gigahertz. So you hit it at 5 gigahertz, at 2.4 gigahertz, it starts dancing around, it gets hot. So your food gets hot and you can have your lunch. When that radiation is coming from Wi-Fi antenna, it gets hot, but it doesn't go through. So if you put a Wi-Fi antenna and you stand in front of it, your stomach is going to get hot and nothing is going to come out the other side, okay? Because you're 75% water. So physicists knew this. So when the government agencies said to them, what spectrum do you don't care about? Like it says junk. Nobody wants it. What's that spectrum? Oh, they said, yeah, 2.4 gigahertz, 5 gigahertz, just give it away. Nobody cares. We don't use it. If you walk in front of it, it goes away. What use is this? This is junk. So they gave it a nice name. They call it Industrial, Scientific, and Medical Band. Okay, ISM band, which means you can't pay for it. And if anybody wants to use it for scientific purposes, just go for it because nobody wants this, this horrible stuff. Okay, nobody wants it. So they did it, and in 1995, the FCC announced, all right, anybody wants this junk, take it, because we're not going to regulate it. It's not worth regulating. Well, who wants an antenna? You walk in front of it, it goes away. We don't want this stuff. Just take it. And maybe I'll make it part of the break because this is a very interesting story. There was these guys in the Netherlands who were working for a company called NCR, National Cash Register. Do you know what a cash register is? You go in a store and they ring up the thing and it tells you how much money you paid for in your groceries. That's made by NCR. NCR wanted to do this thing. They wanted to have the cash register link up to the back office in the grocery store so that when you rung up something, it would allow you to, in the database, it'd say, yeah, you bought 10 cans of whatever, tuna, something like that. To do that, they wanted to use wireless. And the wireless technology that was being used was from IBM. It was proprietary, and IBM wouldn't tell NCR what it was. So there were these 4 guys out in the middle of in the Netherlands who said, okay, we'll just reverse engineer it. And they reverse engineered it. They figured out how it works. And then in 1995, FCC said, use ISM. We don't care. We don't need it. And these guys said, hey, it's free. Let's go use it. And what they did was they didn't know how to build chipsets. So what they did was they took the 802.3 chipset, the Ethernet chipset. And they said, you know what, if I take the chipset and I fake a collision each time I don't get an act back, it looks as if it's 802.3. I can fake it. And so they took the 802.3 chipset and they faked the collision, okay? And by doing that, they were able to get, on the ISM band, they were able to get something that they call WaveLAN. Okay, and WaveLAN was a product that came out of, by that time NCR got acquired by AT&T, it was called AT&T. WaveLAN came out in 97 or something like that. It was the first wireless system. And WaveLAN became quite popular. WaveLAN 2 came out, other people said this was pretty good, and IEEE standardized it as 802.11 in 1997, and that became known as Wi-Fi. Okay, industry consortium called it Wi-Fi. Wi-Fi was not based on OFDM, it was actually based on what's called frequency hopping spread spectrum, but it's not important. We can fast forward a few years later, you know, to now. We have 802.11 A, B, G, N. As you know, this was B was the oldest, and then we had A, and then G and N. G and N, which is what most people use today, are both OFDM, which is what's using this over here. And we're still stuck in that horrible spectrum. We're still in the 2.4 gigahertz and 5 gigahertz spectrum, because that's what they started out with, and that's the spectrum you can use. So you have a laptop over here, it's on 2.4 gigahertz, you don't need a license for it. On the other hand, if you set up a radio station to broadcast, you can't do it on the 700 megahertz band, for example, which is used for TV, or 800 megahertz band. You have to do it somewhere else. And you have to pay a lot of money for it. If you try to broadcast on 800 megahertz today, you'll be sent to jail. Okay, that's what will happen. People will detect you and send you to jail because you're interfering with the so-called public carriers. So if you want to interfere, 700 megahertz was auctioned 2 years ago in the US. And if you saw this, Google bid, I think, $12 billion for it. Other people bid more money for it, and so on, and that got sold off. And the 700 megahertz auction is coming up in Canada either later this year or next year, and it'll be $4 or $5 billion worth. So when you pay that kind of money, you want to make sure you squeeze as much as possible into it. And that's why we have this over here, OFDM, and that comes from the nice property of the sinc function, that it has zero crossings at 2m pi by tau. So this little equation over here is worth billions of dollars. So it's not as good as E equals mc square, but omega equals 2m pi by tau is pretty close to it. Okay, and that's what everybody uses today. OFDM is the thing. So this is how math relates to communication and relates to what happens in the real world. Okay, so I had a different story for you, but I think I'm going to keep this as a story because the other one is also interesting. I'll talk about it next time, perhaps. Any questions about any of this so far? Yeah?
What happened with the 2 there?
What happened with the 2 there? Which 2 there?
Between sin and sinc.
Sine and sinc. Because you have to divide by 2j to get this. To get sine, I have to get the 2j over here.
No, after sin, because if you're going from sin to sinc,
yeah,
you have to divide it by omega tau by 2, right?
Right, so this is multiplied by omega tau by 2 on the numerator, sorry, tau by 2 on numerator and denominator, right? And so I'm sorry, this should be 2 sine omega 2 by tau, because this divided by 2j is going to be sine. I need to multiply by 2 to get the sine here. So e to the x minus e to the minus x by 2j is sine, not by j. So I have a factor of 2 from the. Okay. So e to the j omega minus e to the minus j omega by 2j equals sine of omega. So I have that factor of 2 coming from there. Right? So I need the 2. To get the sine, I need the 2 over here, because I'm going to multiply and divide by 2j over here. So I need to do 2j and 2 like this. Then I get 2 sine omega tau by 2 omega tau by 2. So I left out the 2 on top. Okay, let's do it after class. Okay. Don't worry, I checked this pretty carefully. I think I'm pretty okay with this. Okay, now that we've got that settled, let me move on to the properties for the Fourier transform. I'm going to actually start with what I call the Dirichlet conditions. So the short story about Fourier is that he was studying heat transfer, and he came up with this Fourier transform as a way to figure it out. And he wrote a paper about it, and was submitted for a prize. They're going to give the best paper prize. And the 2 other people on the panel to look at the prize were Laplace and I believe Legendre. And the 2 other people whose names did not begin with L. Okay, but these guys are really great mathematicians, and they saw this paper and they said, it can't possibly be true, because you're saying you can do it for any function, and in fact it doesn't seem to work when you have discontinuous function. And Fourier said, oh no, I can patch up the analysis, I can take the limit the right way, it's all going to work. And Laplace and Legendre were not convinced. They said, sorry, we can't publish this paper, and they didn't. 15 years later, he finally got it published. Okay. And but it was messy. It wasn't really very clean. And quite a bit later, Dirichlet figured out the conditions under which under which the Fourier transform exists. Because you see, the Fourier transform is supposedly for any function whatsoever. What about stuff that looks like this? I mean, you can define, that looks pretty messy. Okay, what about functions that are pathological? You can say that in any period of time, they have an infinite number of zero crossings in any period of time. Okay, and we can actually define those functions. If you put your mind to it, you can define very pathological functions, and people have done that. And they found that for those things, Fourier transform actually did not exist. So anyway, so what Dirichlet did was he said, okay, you need two conditions under which, if these two conditions are met, these are necessary, these are sufficient but not necessary. Okay. In other words, if these two conditions holds, for sure we're going to have Fourier transform. If they don't hold, we can't say, right? The first one is that xt is absolutely integrable. Which means that it's defined to be minus infinity to infinity. Modulus of xt dt is less than equal to, is less than infinity. So in other words, the total area under the curve, the total energy in the signal, if you can think about that, is going to be finite. You can't have infinite amount of energy, so you can't have a signal that keeps growing over time. It has to be finite. And the second thing is that has a finite number of maxima and minima and finite number of discontinuities in any finite interval. So if I have some function, thing like that, okay, the area under the curve is going to be small. I can even allow some number of discontinuities. Okay, I can have this here, I can go down and then jump back up again and so on. But the number of discontinuities in any interval should be finite, can't be infinite. And because, as I said, people are coming up with these bizarre functions which have an infinite number of discontinuities in a finite interval. Okay, so that didn't really work so well. So Dirichlet showed that if these two conditions hold, then we're going to have a function. Then you're going to have Fourier transform defined for that. Okay, and so how does it work? Well, we don't need to worry about that. And these are in fact satisfied by most practical signals. Okay, and so generally speaking, if you're going to compute the Fourier transform, you should, for completeness, make sure it satisfies the Dirichlet conditions. Okay. Now the Dirichlet conditions are sufficient but not necessary. So I'm going to show you an example where we have a function which is highly discontinuous. Okay. Actually, it satisfies Dirichlet conditions, I guess. It's kind of hard to tell. Okay, let's see. Let's get delta t. We say that the area should be less than infinity, so we know the area is 1, so that's fine. Finite number of maxima and minima and finite number of discontinuities. It has one discontinuity, so I guess delta t does satisfy the definition of the Dirichlet conditions. But at any rate, let's go and compute the Fourier transform of a impulse. So again, we just go to first principles. X j omega is given by integral minus infinity to infinity xt. Xt is e to the minus j omega t dt, and this is going to be nothing more than minus infinity to infinity delta t e to the minus j omega t dt. Okay. Now I'm going to remind you of a fact that I wrote down a couple of lectures ago, which was that x tau is going to be given by minus infinity to infinity x t, it's t over here, not tau, delta t minus tau dt. Okay, so this is the kind of the convolution definition. Okay, for the and I'm just changing where I swapped tau and t, and I said you can write it this way. So let's look at this one over here. So we have e to the j omega t delta t. So if you compare these two, we find that this integral can be just written as e to the minus j omega tau in the range minus infinity to infinity. Okay. Sorry, I take it back. What am I doing? At 0. Okay. So this x of tau. So tau equals 0. Let's just write it out. Tau equals 0. Then we see x of 0 equals minus infinity to infinity x of t delta t dt. We're just setting tau equals 0, right? And so if you match this one and this one, we just want to find e to the j omega, e to the minus j omega t at tau equals 0, and this is going to be just 1. Okay, and so we can write this in this fashion. So I didn't show you the notation. So we write this. The notation for transform is that xt, and we use script f x j omega, which means that the function xt, the Fourier transform corresponds to the function xj omega, which is a function of omega, not of t. And so here we can say that, what do we say? We say that x we have delta t, and its Fourier transform is 1. Right? And we get that just from first principles. And so even though delta is kind of this funny function, we don't have to evaluate the integral kind of directly. We do it using this definition of delta integral, and that gives us the value of the Fourier transform. Okay. Any questions about this? Okay. Let's do this. Okay. So the next thing I want to define is the inverse Fourier transform. And this I just define. What we want to do here is to go from right to left, and we define that as xt equals integral, 1 over 2 pi integral minus infinity to infinity x of j omega. It's going to be j omega e to the j omega t d omega. Right? So we have a function of omega, we have to do d omega. And it looks a lot like the Fourier transform, right? We have minus infinity to infinity, we had xt e to the j omega t dt. Here we have j omega t d omega, and we're getting xt out of it, except there's this 2 pi kind of factor that you have to worry about. But other than that, it looks very much like it. And if you look at the Fourier series is basically a summation that looks like this as well. There we had essentially ck multiplied by e to the j k omega naught t, right? We had the j k omega naught t, and here's summation. So we had in the Fourier series, we had xt equals summation minus infinity to infinity ck e to the minus j k omega naught t. So what's happening here again is that we're having xt. Forget about the 2 pi for now. We're getting the ck. It just goes away because ck we can't define anymore. Instead, we're getting x j omega e to the j omega t dw. So, and then ck you have to substitute over here. You'll get something similar to this. So, I just wanted to compare the form. We're going from a summation to an integral, and that tells us how to compute the inverse Fourier transform. Okay. Any questions about this so far? Okay. So let's use this. So we're going to say I have a signal. Let's say I have xj omega equals delta omega minus omega naught. So we see this as it's a funny thing. This is an impulse in the frequency domain. Okay, it means that with delta omega is like delta t. Delta t means at time 0 we have an impulse. Delta omega is that at frequency 0 we have an impulse. Okay, in fact this one is a frequency of omega naught. I have an impulse. Okay, so I can just draw this line, and this is omega, and at omega naught I have an impulse. Okay, and what does it mean to an impulse in the frequency domain? at omega naught, what this means is that at that particular frequency, I'm going to have an infinite amount of power and unit amount of energy, okay? And that's basically what it is. So if you think of tuning your radio channel, and when you tune your radio channel, what you're doing is you're choosing the resonant frequency of the circuit that is detecting the radio waves, right? So you're choosing the natural resonant frequency of the tuning circuit, and you turn it to a particular value, omega. If you're at delta omega at, let's say, 5 megahertz frequency, when you turn it to 5 megahertz, you'll get a very loud noise, okay, because you have essentially infinite power at that particular value. But it's very, very limited. You change it slightly beyond, you won't get anything. Okay, even infinitesimally beyond the omega naught, you'll get zero power, but at omega naught, you'll get essentially infinite power. Okay. So that's the meaning of omega naught. So we can actually use this, the inverse Fourier transform, to compute this. So how do we do this? Well, xt is given by definition as 1 over 2 pi integral minus infinity to infinity xj omega, which is delta omega minus omega naught e to the j omega t d omega. And the thing is that we can now use the same trick over here, right? We're just going to set we can use the same trick over here to say that this is equal to e to the j omega naught t. Okay. Why? Because over 2 pi. Okay. Why is this? Because we are going to have this equation over here, x of 0. Okay. Sorry, we don't say t equals 0. We just say x of tau equals xt d t minus tau. I can just replace basically t with omega and tau with omega naught. Okay, because this is symbol substitution. So I'll get x of omega naught equals integral minus infinity to infinity x of omega delta omega minus omega naught d omega, right? I've just substituted tau as omega naught, t as omega, and then this equation continues to hold because substituting symbols doesn't change it, right? It's just symbols. So then if I use this, I just plug it in over here. So e to the j omega naught t is what I'm, by 2 pi is what this is going to be. xt is going to be this. Okay. And that gives us the value, that gives us the homework assignment. So I said that, so we can write this like this, e to the j omega naught t by 2 pi delta omega minus omega naught. We just set omega naught equals 0. This implies that 1 over 2 pi it corresponds to the frequency delta omega. Right, so the inverse Fourier transform of delta omega is 1 over 2 pi, the constant 1 over 2 pi, and that was the solution I was looking for. Okay, and again you just plug essentially omega naught equals 0. Okay, everybody got that? Okay, so now we are ready to talk about the properties of the Fourier transform. Any questions about this so far? Because I just showed you right now the forward transform and the inverse transform, and now we're going to use the forward and inverse to compute some properties. Beg your pardon?
Can you leave the last one for a second?
Yeah, sure, I can do that. Yeah, no problem. I'll leave the inverse up actually for you. Okay, so there are some properties of the Fourier transform that make it really nice, and I'm going to write down the couple of properties and then a run out of time, and then we'll continue with the properties next time. So the first property is what's called linearity. We always like linearity because it allows us to do easy math. So we say that if x1 t has a Fourier transform of x1 j omega and x2t has a Fourier transform x2 of j omega, then ax1t t plus b x2t. This whole thing has a Fourier transform of a x1 j omega plus b x2 of j omega. Okay, so we're just saying that if I take two functions, I can multiply them by value a, scalar a, and then the transform is multiplied by scalar a. Well, why is that? Because, well, it's pretty straightforward. Basically, x of j omega is nothing more than the integral minus infinity to infinity xt e to the j omega t dt. So if I multiply by scalar by a, well, obviously the integral can pull the a out of the integral sign, right? So that's where we get that. Similarly, if xt is replaced by xt plus yt, well, we know that integrals sum up, right? Integrals sum up. You can take the area under the sum of two functions is the sum of the areas, because integrals sum up. So because integrals sum up and because integrals scale, so do the Fourier transform. So we get linearity essentially as a trivial property of the Fourier transform. And we can use this for some interesting stuff. So let's compute the Fourier transform for cos omega naught t. So what's cos omega naught t? Well, cos omega naught t is a sinusoidal, and its frequency is omega naught, right? So it's a phasor, right? It's the I should say it's the value of the phasor, the value of the distance from the y-axis of the phasor at time t, where the phasor is rotating at angular velocity of omega naught radians per second. Okay, so a phasor rotating omega naught radians per second. Look at the distance from the y-axis. That's this horizontal distance. That's cos omega naught t. So using Euler's formula, we can write this: cos omega naught t is equal to half e to the j omega naught t plus e to the minus j omega naught t. Okay, and so that's good. So now we have a half and we have a addition. So we can write, so the Fourier transform of this is going to be given by half the Fourier transform of e to the j omega naught, so omega naught t plus half the Fourier transform of e to the minus j omega naught t. Okay, but I just showed you that, where did I show you? That e to the j omega naught t corresponds to, okay, where did I put this now? Okay, so e to the j omega naught t corresponds to 1, right? By 2 pi. That is what we did just a moment ago. So we know this, so we can use this and this fact over here plus this one over here. So this Fourier transform corresponds to basically 2 pi. This corresponds to, sorry, it's not, what am I doing? Okay, wait a minute, I better get this right. So the e to the j omega naught t corresponds to 2 pi, delta omega minus omega naught. Okay, so we get from here that this one is going to be half 2 pi delta omega minus omega naught plus half 2 pi delta omega plus omega naught. And I'm completely lost away. Okay, sorry, I'm looking at the wrong one. Yeah. And so we're going to get over here. So we're going to get over here cos omega naught t corresponds to with the Fourier transform corresponds to pi times delta omega plus omega naught plus delta omega minus omega naught. Okay, and this is just from this over here. So basically this is a very common trick, you should remember it. Whenever you see cos, immediately go into Euler transform that gives you exponentials. Exponentials, you can very easily get the transform as a delta. Okay, this is what we got last time from the previous example, which I think I left up there. So e to the j omega naught by 2 pi corresponds to delta omega plus omega naught. This is what I used over here. So I'm just rewriting that over here. Okay, I'm just moving 2 pi over because I can always do that because of linearity. And then I get cos omega naught t corresponds to this. So the way to think about it, and I'll stop with this, is that when you have a sinusoidal, okay, we can think of it as being generated by two phasors. Okay, if you look at these two guys, so this is omega plus omega naught, omega minus omega naught are delta functions which are at plus omega naught and minus omega naught. Remember, we write a delta with this arrow pointing up, and so these are two impulse functions in the frequency domain, okay, which are at these values, and we can sort of think of them as having sort of two counter-rotating phasors, okay, because one is positive frequency, one is negative frequency, and that's the one I showed you. If you take two phasors that are in opposite frequencies, then you add them up, what you get is a real function of time, which is in fact a sinusoidal. So these, if you remember those two balls going round and round, those two phasors, they cancel out, and what you get is just a simple sinusoidal, a cos omega naught t over here. Okay, so in some sense, what the Fourier transform is doing is taking a real function of time and figuring out what phasors at what frequencies can be generating it, would be generating it. Certainly, that's what we're doing with the Fourier series. The Fourier series, a periodic function. We're saying these are the frequency components, the harmonics are generated. In the Fourier transform, we are in this case, we just have two terms. It's like a Fourier series only has two. Why we only two terms? Can anybody tell me why you only have two terms for cos omega naught t? Yeah? Did you have an answer?
Yeah, because it has only the frequencies of plus or minus.
Well, I want a better answer than that. Why does it only have two terms for cos? Yeah?
Because we go to the imaginary part to cancel out.
No, even simpler answer. What is cosine? Cosine is a periodic function, right? When cosine is a periodic function, we know its Fourier series has to be, it just has a finite number of terms. Not finite number of terms, it has discrete terms. In this case, it turns out to be just finite number of terms. In Fourier transform, you could have infinite number of terms, right? It's a summation. But when you have a periodic function, we can apply the Fourier transform to it. We will typically get something nice and simple because it's just a small number of terms, right? Because in fact, we only have two terms over here because it's a periodic function. If you had an aperiodic function, then the Fourier transform can be more complicated. But a periodic function, the Fourier transform is actually quite nice and simple, which is what you're seeing over here. In fact, it's just a couple of deltas. Okay, I'll stop here, and we'll continue next time with some more properties of the Fourier transform, and maybe we'll get to Laplace. We'll see.